One of the ways that you can speed up a reaction is to increase the temperature. So therefore, the rate of the reaction is dependent on temperature. But if you think about the rate law doesn't have temperature as one of the variables. What it does have is the rate constant. One of the facts about a rate constant is the rate constant is only good at one particular temperature. So what's going to happen to the rate constant if you start changing temperatures? Well, it changes. And whether it's an exothermic or an endothermic reaction, if you increase the temperature, the rate constant is going to get bigger and bigger and bigger because increasing the temperature increases the rate. So there's an equation that was developed, and it's referred to as the Arrhenius equation. It's named after the man who helped develop this. And what you can do with the Arrhenius equation, which I have right here, is it shows you the relationship between the rate constant and the temperature. But there are also some other factors involved in a reaction. One of those is what's referred to as the frequency factor, and it has to do with the collisions. In order for a reaction to occur, the chemicals actually have to collide, so that then their electron clouds might have the potential to change and form new bonds. Break old bonds, form new bonds. And so the more collisions, the bigger this frequency factor. It's that number of collisions that occur. And then this E is the inverse of the natural log function. So that is a number. And you raise E to the negative E sub A. And E sub A is just our abbreviation for activation energy. Activation energy, the amount of energy it takes for the reactants to form this activated complex where the bonds are ready to break. So exothermic, endothermic reactions, both of those, you have a activation, a positive amount of energy that's needed so that the bonds that are present for the reactants begin to break. That activation energy divided by R, which is a gas constant, and it's the gas constant for energy, not for the ideal gas law. And then also divided by temperature, but temperature's in Kelvin. So right here is that temperature variable. So as this temperature changes, the rate constant changes. Well, if we actually do a series of experiments and you change the temperature and you measure the rate by measuring concentration changes and time changes, then you can actually figure out the rate constant at different temperatures. So what we have here is we have some data. The temperature at 440 degrees Celsius, 460 degrees Celsius, 480 degrees Celsius, and 500 degrees Celsius. And then you have the rate constant at each of these temperatures. And you notice as the temperature goes up, the rate constant is getting bigger. So this experiment that was conducted, it is just the initial step in the formation of smog. The initial step is the combination of nitrogen and oxygen to form nitrogen monoxide. And so this chemical reaction is nitrogen gas plus oxygen gas, and it forms 2 moles of nitrogen monoxide gas. So there is the balanced reaction. We have a coefficient of 1 for nitrogen, and a coefficient for 1 for oxygen, and a coefficient for 2 for nitrogen monoxide. And so if this initial step is an elementary step, then we should be able to write the rate law, because for any elementary step or single step in a reaction, whatever the coefficients are, that is also the order for each chemical. And so to write the rate law, you just type or write rate equals the rate constant, and then that will be times your first reactant raised to its coefficient, and then your second reactant raised to its coefficient. So there is the reaction, and because we were told that it was single step. And then just again, if it says that it's the initial step, then that's just one step in the process that occurs. But by saying it's single step, we can take the actual reaction and use the coefficients as the order. So it is a second order overall because the individual orders are 1 and 1, and the overall order is the sum of the individual orders. So this is a second order reaction. It's dependent on the concentration of nitrogen and the concentration of oxygen. So we're going to now use the data below to determine the activation energy. So the initial information is not really related, but in order to actually figure out the rate constant at each temperature, there would have to be each individual experiment, one at 440, one at 460, one at 480, and one at 500. You would have to measure the initial rate and what concentration of each of these chemicals there was at that particular rate. And then you could use that information to find K. So each of these Ks would have been calculated by taking time and concentration data for this experiment. So use the activation energy and frequency factor. And so in order to use the data to calculate the activation energy and frequency factor, I should say. So this equation here is just one rate constant, one temperature. But you can actually mathematically alter this. Take the natural log of both sides, and you end up with a linear function. And so this linear function, you have the natural log of K is equal to, so the natural log of K, the natural log of your rate constant, that is going to be your Y value. And that is equal to negative E sub A, the activation energy, divided by the gas constant. That's going to be your slope, times 1 over the temperature, that's your X value, plus the natural log of A, that frequency factor. The natural log of A is going to be the y-intercept. So y equals mx plus b. This format. So in order to look at a linear relationship occurs in a graph. So we actually have to graph. And what you graph is you graph x versus y. And so I have to graph x, which are going to be the temperatures, the inverse of those temperatures, versus the natural log of the rate constant. And so to get a graph, you need to use some kind of spreadsheet. So I use Excel, but you can use Google Sheets or other forms, as long as you can put the data in and alter the data and then form a graph. And so what you want to do is you want to plug in the data that you're given. So I have plugged in the Celsius temperatures and the rate constant. And what you want to do is not only plug in this data, but you also want to put headings so that you know what the data is that you have entered, because we want to use this data. And so what we want is we want to graph x versus y. So our x value is 1 over temperature, but the temperature has to be based on temperature in Kelvin. And so you want to look at your data and you want to see, is my data in Kelvin? And the data that we were given was in Celsius. And so I am going to change the data and make it be data that is going to be in Kelvin. And so in this next column, I'm going to type in temperature, and then I'm going to put Kelvin. And I'm not going to use capital K, simply because sometimes capital K gets confused with little k rate constant. So I'm just going to put Kelvin. And so the Celsius temperature plus 273 will give us the Kelvin temperature. So I'm just going to have Excel do this for me. So in this cell, what I want it to equal is my Celsius temperature, which was in this A2 cell, plus 273. And so the temperature in Kelvin is 713. And if you want the data to continue on so that each of your temperatures is the temperature plus 273, you can go to the cell that you created that equation in. So I have A sub 2 plus 273. If I drag it down, it then does A sub 3 plus 273, A sub 4 plus 273, A sub 5 plus 273. So each of the cells now is the original temperature from over 2 columns over plus 273. So now I have the temperature in Kelvin, but I'm still not quite there yet. What I want is I want the Kelvin temperature as an inverse, and that's going to be my X value. And so since my X value is not quite ready, I'm going to create another column, and this column is going to be what my X column is. So I'm going to put X value, and the X value is going to be 1 over temperature. And so for that X value, I want that X value to equal 1 divided by my temperature. So you can just tell the cell what you want it to be in there. You want that value to equal 1 divided by that temperature. So I went over and I just touched the temperature value in Kelvin, and I'm going to hit enter. And there is the value of the inverse of the temperature. And so again, because I put in a math equation, you can repeat that math equation all the way down for all your data. And so I drug the equation down to where it's even with our last data point. And so this is my X value. Now the Y value, I want the Y value to be the natural log of K. And what I have is just the rate constant. Not K Kelvin, but K rate constant. So what I want the Y value to be is I want the Y value to be the ln of the rate constant. So in this cell, I want it to equal, make it a little bit bigger so you can see it better. You want it to equal ln, and then you want it to be the natural log of your rate constant value. And there's my first rate constant value. So I'm going to go over and touch that cell and then hit enter. So this value is the natural log of the rate constant that was at the 713 Kelvin temperature. And again, because I used a math equation and had an Excel spreadsheet do this for me, I can repeat this math equation by going and touching the cell, going to the corner when you see the little T shape, and you just drag it down. And so now I have repeated this calculation for each of my rate constants. So now I have my X value and I have my Y value. And with this, you want a graph because you need the slope and you need the y-intercept. So we want to graph this data, and so to graph the data, you go up and you choose Insert, and you're going to choose a scatter plot, so just the data points. And you see there's one data point that is in the wrong place. And so let's go back and see if there was, looks like my temperature here doesn't match up with an increase in temperature. So let's go back and look. Oh, okay, so I have a temperature that's lower, so I must have typed this in wrong. So I should have typed in 480, but I typed in 450. So I'm going to change this to 480, and it should change everything. And so if we go back and look, it changed this one became larger, and then you have this data, and then it changed all the temperature data, and it evened out my line. So anytime you get to this point and you're pretty sure that you have the right X and the right Y, so we went through and we made sure my X is this value, my Y is this value, and I had Kelvin. If you have one data point that just isn't in the right place, the first place that you want to look is you want to look back and make sure that you typed in the data correctly. And you don't have to start over. If you typed it in incorrectly and you change it at the original value, then it will change everything that's tied to that. So now we have what looks like a linear relationship. So you want to go in and you want to highlight one of the data points, and you'll see this pop up on the side. And what you want to do is you want to add, that literally means add, and you want to add a trend line. So let me go back over here so you can see the whole thing. So we're going to add a trend line, and that's one of the choices. And so it puts a trend line through it, and you can see that the line almost goes perfectly through that, but not quite perfect, but that's fine because these are experimental values. So it looks like a pretty good linear relationship, and so we have a trend line, but what we want from any of these trend lines we create is we actually want the equation. And so we're going to go in and we're going to choose more options. I'm going to show you what the more options look like. And so you've got the format the trend lines over here on the side. We need to display the equation on the chart, because what we want is we actually want this equation. The whole point of us doing all of this is we want the equation, because what we want is we want the slope and we want the y-intercept, because the original question was determine the activation energy and frequency factor. Well, activation energy is part of the slope and frequency factor is part of the y-intercept. So I need the slope and I need the y-intercept. So let's go back and let's look at this. So we graphed the data. We put the data in a scatter plot. It wasn't quite linear because I made a mistake on what I typed in there, so we just go fix the mistake, and that makes it linear. Then once we add a trend line, we display the label, because the label will give us the y equals mx plus b. So I'm going to write this y equals mx plus b down, and then we're going to label all the data. So y equals negative 24,371x plus 28.204. Okay, so if we look, we have, let's line it up. Y is ln of k. That's what we graphed. Y value ln of k. Our slope is negative e sub a over r. So this slope is negative 24,371. That's the same thing as e sub a over r. Our x value was our 1 over temperature, and the 28.204 is the natural log of a. So if we just take our slope data, our actual slope, and we plug it in right here, the slope will be our activation energy times negative 1 divided by r, and the gas constant for r is 0.008314 kilojoules per mole. So let's take our slope, negative 24,371, that's the slope data, and that is equal to negative e sub a over the gas constant, 0.008314 kilojoules per mole. So our unknown is activation energy. We have the slope value and we have the gas constant. So just rearrange this equation. And you get 24,371 times the gas constant. You get 202.6. The the negatives cancel because you divide by a negative and you get a positive. So the activation energy is equal to 202.6, and the units would be kilojoules per mole because that comes from the gas constant. This is a positive value, positive activation energy. Then you also are going to take the y-intercept value you're going to take the y-intercept value and set it equal to the natural log of A. So our y-intercept was this 28.204. So in place of y-intercept, you're going to write 28.204 equals, and that's equal to the natural log of A. So again, these two equations, we're just taking values from our linear equation. And so you plug in what the slope is right here where the word slope is, and then you set it equal to negative E sub A over the gas constant. And then you take the y-intercept data, plug it in right there, and that's equal to ln of A. So we have 28.204 equals ln of A. So A is our unknown, so we do E of both sides, and that will cancel out the ln. And so A is E raised to the y-intercept. So we have E and we're going to raise it to the 28.204 power. And so we get 1.77 times 10 to the 12th. And that is the frequency factor, which is the number of collisions that happen per whatever the time period is for this experiment. And so A is the frequency factor. And then E sub A is the activation energy. And so our activation energy is positive 202.6 kilojoules per mole. So we use the graph to get our y-intercept and our slope so that we could find activation energy and the frequency factor. And this is how we would use that Arrhenius equation. And so the last question of this problem is we want to use our graph or mathematical equation. So graph would mean you would look at this graph and you would extrapolate where 600 degrees Celsius is. Or we can just use the Arrhenius equation, which is this equation. This equation is not really for graphing. This equation is just for one data point. And so we want to figure out what the rate constant is at 600 degrees. So if we take our y equals mx plus b, then we know what the slope is. The x is the inverse of the temperature in Kelvin. This is our y-intercept. And then y would be the natural log of k. So let's plug in our data. Natural log of k is equal to we have a constant slope of negative 24,371 times 1 over t plus 28.204. And so in this question, we're told that the temperature is 600 degrees Celsius. So 600 degrees Celsius, we need to put that in Kelvin. So natural log of the rate constant is negative 24,371 over 1 over 873, because that is 600 degrees Celsius in Kelvin. And then we're going to add the 28.204. So if we do the calculation on the right side, then we would do 24,371, and that's a negative. Negative 24,371 divided by 873. So that would be negative 27.916 plus 28.204. So we're going to plus 28.204. And so the natural log of K is 0.2876. So we do E of both sides. That allows us to figure out what the rate constant is. So we take our value here, and we're going to have that be our exponent for E. So we do second E, and we raise it to our answer from a previous section. And so we get 1.33 for our rate constant. And if you take a look at the data, we're at 500, we're going up in increments of 20, and we're up to 0.0393. So the rate constant goes up as the temperature increases. And so 600 degrees is 100 degrees more than that 500. And we got a rate constant that is larger, not a huge amount larger, because 1.33 and then 0.0393, that is quite a bit larger, but it is not in the hundreds larger. So you didn't get 100 and something. We got 1.33 as the rate constant.